Today I will be talking about diffraction processing using IPLT. Some of you already saw it yesterday in the hands-on practicals. So we get now a little bit more details on what is going on in the background behind the graphical user interface, how the things are done. For the rest of you that hasn't seen it yet, there will be also an introduction on how the graphical user interface works. And you will see it in this afternoon in the practicals. So what I'm focusing on is here that part. So really, diffraction processing. In the talk this morning, here just basically this first arrow to get from your raw diffraction patterns to a set of reflections. Then in the afternoon there will be another talk which deals with all the scaling and merging, and how you get a set of discretized data points that you can afterwards use for molecular replacement, or to combine it with image data set, to combine it with phases from there and generate some 3D density map. Okay, so the IPT has a graphical user interface you can use for the basic processing. There is in parallel, there is also a command line interface if you want to go into more details, try things out, want to have tighter control on what you do. So this gives you really the high level overview and gives you the easy processing. But still, depending on the project, chances are good that not everything works automatically. So you have to check it and then go more to the command line interface and have a look at the steps in detail. So the graphical user interface is split into 3 pages. So first page is here the project page. Here on top you can switch between the different pages. So there is one for the whole project, one for processing the individual diffraction patterns, and one for the merging. IPLT saves all the parameters that are used for the processing in one single XML file. And here in the graphical user interface, you can change all these values. You can also change it in a text file if you want, with the text editor manually. And these are used project-wide for all of the diffraction patterns. You have afterwards the possibility, if you have to also modify these parameters for individual patterns. So if you have some pattern that needs some tweaking for the processing, you can do that. Okay, and here on the right side, you have basically all the actions for the very high level processing. So you can add new diffraction patterns. You can define your beam stop mask. That's the thing you have to do once if you are working on one microscope for the whole data set. So the IPT needs to know the shape of your beam stop, because afterwards it will automatically search for it and then exclude it for all the algorithms that not some things below the beam stop is searched. And there are also then further steps to basically search lattices to verify it. IPT forces you to do that manually, because that's basically the lattice is one of the most important things you need to know about the diffraction pattern, because it gives you the information of where your various spots are, but it also gives you the information on how your tilt geometry is. Because for a diffraction pattern, you cannot determine tilt geometry using by looking for the defocus in different sides of the image. So that's the only source for the tilt geometry. So that's why it's very important to get it correct. So that's why also why you are forced to look at it and verify that it's correct. And then afterwards, you can refine the lattice and extract the data points. There is also then you can merge the data. Here on the lower right, you get some information, some very basic information about the project. So number of images you have, how many images at which tilt angle, and also how many of them are verified. You will see later on the next page, there are some more detailed information about every image. So if you now switch here to actually I should call that probably diffraction patterns page, not images page. That's more because I'm also part software developer, and For a software developer, everything that is a TIFF or a DiM3 file is an image, even if you record a diffraction pattern. So that's why I called it image. Anyway, on that page, basically here, get on the left a list of all the diffraction patterns you have in a project, and you get a summary on how far they are processed. So the beam stop was searched, if the origin was searched, if the lattice was searched, if it was verified, if lattice points were extracted for the refinement of the lattice, if the lattice points were the diffraction spots were integrated, and if the tilt geometry was defined, was determined. So you see here some of them. That's just a small test project I used to generate the screenshots. You see some of them are fully processed, some of the patterns are fully processed, and some of them here are yellow. So this part here is not yet done. So that's the first part here, where you really get a list of with indicators of your processing status. And you also have here a check mark. So if you see that you have a bad diffraction pattern in there, it's very easy to exclude it from further processing and merging. Here, that's very similar to the one to the panel we had here in the merging, in the project setup. Here you can set basically the processing parameters that are used to define the lattice, to extract the lattice, extract the data points. But if you set it here, it's just for the one image that is active, for the one pattern that is active. So here you can really tweak for every single pattern to get an optimal processing. And you can always, if it doesn't work, you can always reset it to the global value you set for the whole project. Here you also get a list of actions for every diffraction pattern. This is now a little bit in more detail. So here you can really run every step manually. Whereas here on the, if I go back on the project page, basically the steps were put together. So it just runs as much as possible until the next manual step. And here you really have the chance to go through every step manually. And then also you get a results files and log files for every step, so that you can really verify that all the steps went right, that the program really did what it should do. Okay, yeah. This here already mentioned. Here down below you have all the log files, and also other. Sometimes you also get result files. For example, you get a difference vector image, which was used during the lattice search, so that you can have a look also at the difference vectors and see if the lattice search did the proper thing. Okay, so that's now an overview of all the steps that are needed to basically extract your data from one diffraction pattern. First, you need some prep step, which basically adds your image to the project, generates an XML file where you could store the parameters that are that are specific for that diffraction pattern, and so on. So in the graphical user interface, that's this button add images. If you do it on the command line, you can just basically do an IPLDiff init, then it will generate these files. The next part basically deals with finding the beam stop and finding the origin and finding the lattice. So in the graphical user interface, these are put together into one procedure, but you can also, either on the diffraction pattern page or on the command line, you can also run them step by step. The first part here, the beam stop mask finding, that's basically it's a little bit simplified if you do it like that. So it's basically it's a cross correlation search of the shape of your mask on your diffraction pattern. So it basically finds the position of the beam stop mask in each of the diffraction patterns. Because depending on how you set up the microscope, normally the shape of your beam stop doesn't change, but the position might change slightly. Yeah, okay. You can also run all these steps together on the command line with doing an IPLDiff all. Then, okay, the second step is here is searching for the origin. One problem you have if you process diffraction patterns is that you have a lattice, but you don't see the origin of your lattice, because there you have basically the beam. You have a very intense beam of all the electrons that were not scattered, so you have to mask it with a beam stop. This is a little bit of a problem because then you cannot directly determine the origin because it's always below the beam stop. So what we do is we basically we fit the background of inelastically scattered electrons and extrapolate that where there is the highest intensity in the inelastic scattered background. There should be the origin. So that's done to basically find the origin of the lattice. Then the step afterwards is just searching the lattice itself. I will come through all the steps a little bit in more detail and show you how it is done afterwards. And after having searched the lattice, there is a manual verification step. So it will not run completely automatic. You have to check there that the lattice is okay. And also you can also check if the beam position was found okay. That's very important because if you just have a set of points and define lattice, there are several ways you can index the same lattice that you basically cover all the spots. But depending on how you index it, you might end up with a completely different tilt geometry. So you can completely index it wrongly and still get the same lattice in the end. And the program, especially for tilted diffraction patterns, not necessarily can know which one is the correct one. So that's why you need to have a look at it and really verify that the lattice is correct and that the indexing is correct. Afterwards, the rest of the steps can be run just by refining lattice and extracting data. And you can also, on the command line, either run it step by step or run it with a second IP diff all. So what is done there is here for after manual verification, for each diffraction spot that is found, there's a profile fit to fit its exact position. With this, the lattice is refined to get a more exact lattice, and afterwards the lattice peaks are integrated. So you get for every peak you get a intensity value and you get also a sigma. And then as last step, the tilt geometry is defined. So basically this uses the refined lattice, and from this calculates the tilt geometry and gives you here, in addition to the HK, gives you also the C star value for every diffraction peak. And afterwards, the data is symmetrized and can then be used in a later step for merging. So, as I said before, you have a beam stop. You have to know its shape. So in the graphically useful interface, you can basically define a polygon going around your beam stop to define its shape. And then the program will, for every pattern, automatically search for a translation of the beam stop. The second step is the origin. The origin are fitted based on the background intensity. It's only an approximate origin, so it can happen that sometimes it's one index off or so. So that's also a reason why you have to do the manual lattice verification. Okay. So then lattice search. That is done by doing a peak search on the original diffraction pattern. Then you get a set of peaks. Some of them will be from the correct lattice, but because the diffraction pattern is always noisy, you might also pick up some noise peaks. So then to find the correct lattice from that, what we do is very similar to what is done in X-ray, and actually also what is done in the auto index. It's also a similar concept that we basically look for a set of, we calculate all the difference vectors between the peaks we found, and then generate a new image where we basically put a peak at every position of every difference vector peak position. This has the nice advantage that now for the difference vector image, the lattice origin will always be in the center. So You got rid of the problem that you don't know the origin of the lattice. Then you will get a set of peaks, which is much more clear than the original peak set you got from the original image. But we tried it out, and then we found that depending on the input set of peaks you have, you still get quite some noise in there sometimes. So because of that, we do the same thing. It's the same method again. So we basically search for peaks here, find the strongest peaks, generate the difference vectors, and get a final difference vector image. And here now really you should just have peaks that lie on your lattice you are looking for. And from here you can easily just basically find the two closest peaks that are not collinear, and from that get a lattice. Yeah. To get the fit somewhat more precise, if you fit here if you look here for the closest peak and try to define the lattice, you do a 2D Gaussian profile fitted on that peak to get the position as exact as possible, that we get as exact initial lattice as possible. So next step then is to do a visual verification of the lattice that the program calculated. That's the only task. It has to be done manually. So there you cannot get around of doing it manually. The other step you can do manually, and it's also sometimes a good idea to check really all the steps step by step and see that everything is done properly. But this here you don't get around. So this you have to do manually. Yeah. The IPT has also quite a nice graphical user interface, which can display the diffraction patterns, and on top of it can display the overlays. For the people that haven't seen it yet, they will see it in the tutorial in the afternoon. And you can do most of the things you need to do to get the correct lattice. You can do with very simple steps. So you can swap A and B. You can basically reindex. So if you see, okay, the lattice is correct, but actually my A vector should go here instead of here. So that's basically with the key combination, you can directly change it to this, get the indexing right. Or you can also easily jump around, set the center to any of the lattice points you got. And what is also quite handy sometimes is if there are some symmetries or some crystals where not all of your diffraction spots are very strong. So it might be that if the closest diffraction spots to the center are very weak, that it picks up, that the automatic lattice determination picks up this peak, which is a little bit further out, which is at twice the distance or something like that. This can happen. So it's easily done just to basically have the distance, half the length of one of the lattice vectors to index that. And for the cases if the lattice is really completely wrong, you can also completely reindex it and fit it manually if necessary. But for most of the cases, you just have to do some reindexing, swap A and B around, things like that. Yep.
What is your guide? So if you have a series of, say, 45-degree different patterns, and you get completely wrong indexing, you would have probably a wrong tilt axis and stuff like
that.
So is that the major consideration?
Yeah, that's one of the major considerations. I can show you that. It's just it's on on this slide. So whenever if IPT displays lattice, it also displays the position of the tilt axis. And here on the right, you also get additional information about the length of your lattice vectors, and also here you get the full tilt geometry. So if you have 45-degree image and it's indexed wrongly, chances are very high that you here don't get 45 degrees. So then you can reindex and you directly see here the tilt geometry changing. So you can directly verify that now you have the correct one if you're here at 45. And also, if you have a side entry stage, or I don't know how, for a top entry stage it's a little bit more complicated, but for a side entry stage, you end up having the tilt axis always in the same direction. for the top entry, it depends a little bit on design if the cartridge can be rotated or not. So there it might be that just for one session you have it at the same position. But that's also a very good indication that you basically have the tilt axis for the tilted images more or less at the same position. For untilted images, it's basically random because there you often have a very low tilt of 1-2 degrees, and then tilt axis can be anything. Yeah. So that's basically one of the major things to look out for. Yeah. Yeah, to also quickly go through the rest of the things, this I already mentioned. You have tilt axis, you see lattice vectors, you see all the points. So you have to check if you really have all of the diffraction peaks on the lattice, or if you missed some. Can select part of the image. That's important to change the contrast, because basically what you can do, which is very fast, is you can select part of the image, press N, and then the contrast will change that you see that part you selected very well. So it adjusts the contrast for that part you selected. Yeah. Here on top, you have also can control your overlay. So if you verify the lattice, you normally have two overlays. You have one which basically shows here the position of the beam stop. So this is the gray line here. So you could also move that around if it's wrong, and then save it. And here you have also a lattice overlay. Basically here all the red peaks, which shows you the lattice. And so here you can activate one or the other. You can hide it or show it, so there is a visible flag, or you could also lock it that you don't change it by accident, but that's not used very often. Once you are sure that your lattice and your indexing and your beam stop is correct, you can also save them here, and then basically jump to the next image. Okay, so after the manual verification, the next step is to extract and integrate the data. So you have here a peak, and then what we do is we fit a 2D Gaussian on top of it with it's a 9-parameter Gaussian. So you also fit a background plane, because we saw that it's very important to get some reasonable background. That's used to get basically to get really the subpixel position of your peak, which is afterwards used for refining the lattice. And then after doing that, the second step then is to integrate your peak. So you basically integrate your peak area to get the intensity of your peak. You integrate the areas outside of the peak to get a background measurement. And then you can correct your peak area for the background. And from the background measurements, you also get a sigma value. So what's your variation in that area? Yeah. Then afterwards, last step is to define tilt axis and do symmetrization. So C star is calculated for each reflection. That's quite easy once you have the tilt geometry defined. And tilt geometry can easily calculate once you know the lattice and you know the unit cell of your crystal. Yeah. Basically, we use these before symmetry conventions in IPLC, so this makes it very easy to once you have the final data set, to go into this before and do the further processing, like molecular replacement or whatever you want to do with it. Currently, we have 4 modes to handle Friedel mates. Either you can just treat them independently. This means you keep all the spots and you just assign the sigma based on the background sigma you have. Then there is also the option to merge it, merge the 2 Friedel corresponding spots if they are present, and just keep the ones single where you don't have the corresponding spots. This would be for example, spots here, where half of it is blocked by the beam stop. You can also merge it and discard the ones that are single, or you can merge it and discard it, and then basically recalc your sigma based on the difference between the two peaks. Yeah. This then generates an R-friedel. So you get at the end of the processing, you get a summary for each image. So you get the number of reflections that were extracted. You get the R-friedel factor weighted. You get it weighted and also unweighted if you want. And you get the tilt axis and the tilt angle. So here there's a second possibility. You basically check for all the values and check that all your 45-degree images are really at 45 degree. And you can also check how close the tilt axis, how close the axis position are in the different images. Yeah. So how you would use it in practice? That's now, yeah, you would create a new project. This you do as soon as you open the diffraction processing program. If there is no project file around, it will ask you if you want to switch to a directory where there is one, or if you want to create a new project. So if you will create a new project. Then you add diffraction patterns, define beam stop once for the whole project. If all the data you recorded were recorded from the same microscope. If you have some several microscopes, you would need to define more than one beam stop, probably because it would be different. Then you search for all the beam stop positions and lattices. So basically, if you press this button here, it will search for all the images that are in the project and that haven't yet been searched. So IFT stores all the values it finds, and afterwards it also knows next time it's open it still knows which pattern was already processed. So it will not reprocess these; it will just reprocess the new ones, unless you do it manually and force it to do it. Then you do the manual verification. Then you can do the refine lattices and extract data for all the images, for all the patterns. Then you can basically merge. So there will be a second talk in the afternoon about the merging. Then in the end, use this discretized data set for phasing, or either combine it with image data sets or go for molecular replacement, depending on what you want to do. So, okay, I think, yeah. It doesn't display here. There's a small print. So that's the ideal case. But I strongly encourage you to really check every step. I mean, it's not very likely that using default parameters, just everything will run through and the processing will be correct. So to really get the best results, you should check every step and verify that the processing was done right and that your diffraction patterns are good, and also remove the ones that are bad and don't produce good data. Yeah. So, okay, this I already mentioned mostly in the first slide. You can easily remove data sets if they are not processing right. So you just take out your check mark. You directly see how far every pattern is processed. You can, for every pattern, you can set individual parameters for the processing. So you can have a different set of parameters for every pattern if you need to. Here, as I said before, you can do the steps manually, and you can also check here down check all the logs and check the steps. Yeah. So overall, there are probably around 50 parameters for all the processing steps and merging steps. A lot of them can be kept as default, but there are some that that are essential, that have to be given by the user, or they are usually required to adjust. So you can easily edit them either manually by just opening the XML file in text editor, or also using the GUI. So what is essential is unit cell, basically how you want to call your project. So the 3-letter prefix you see here, and also you have to give manually the beam stop mask. So if you don't give these parameters, the program will not run. That's absolutely essential. Often you also have to tweak the lattice search parameters to get an optimal lattice. and also the size of the peak integration box. Depending on the size of the CCD you have, and depending on the camera length you use to record the diffraction patterns, the size of your diffraction peaks on the CCD might be different. So you should adjust this box depending on the diffraction patterns you have. So that's just a small example of how actually the data file looks like. That part is for finding the mask. So there are several things you can tweak on how the mask is found. So if you work on a shrink image or on the full-sized image, if you want to clip first your diffraction pattern to exclude some very high or some very low values, because sometimes you get just some noise data in there. Yeah. And also, what I also want to show is that basically in the XML file, all the parameters also explains in somewhat more detail. There's also in the GUI for the parameters. If you go with the mouse over each box, there will be a short description on what it does. But if you want to have a more detailed description, there's one in the XML file where the parameters are defined. Yeah. Okay, so now this was the basic processing. Now I come to some implementation notes, how it was implemented. So the high-level processing workflow is all done in Python. So this also makes it very easy if you have to change it for a project of yours, if you need to do some special processing, that's very flexible and extendable. So and then all the steps, all the algorithms are then basically they're a combination of Python and C++. So they're implemented in C++ to make them faster, and then just export it to Python to be used in the high-level scripts. Or you could also, if you want to, we also had some cases where we just did some rapid prototyping. You can also write some algorithm in Python and see then if they're fast enough, it's okay. You can use it like that, or otherwise you can always move them at the later stage to C++ to get the higher speed. And it's also quite easy to inject some custom processing steps if you have a special case. So that's a small example of what we use in our lab. For the diffraction processing, we also so far used for the aquaport the XTP program, which was developed in Japan. And now to be able to compare the processing in IPLT and also in the XTP, I just quickly added an additional page where you can export all your data once you have determined the lattice to the XTP format, and also just in parallel run the processing in XTP to get a one-to-one comparison on how well the programs do. So that's quite easy to add. That's basically one small Python script to add an additional page to do some custom things you want to do. And for the documentation, as I already told you, there's some direct documentation in the graphical user interface. There is in the XML file, the parameters are described. And there is also a web page, apt.org, which describes especially the command line processing in more detail. The new graphical user interface is not yet on the public available website. I started putting together a website for the new graphical user interface because this was done quite recently and will probably be online in the next few weeks. So there will also be some documentation on the new interface. Yeah, just to summarize, we have complete diffraction pipeline to go from individual diffraction patterns to discretized HKL data set. Okay, it's actually HKC star normally because it's not yet lattice line, because there was no lattice line fitting, no discretization. So still here a C star to the reflection list. And it's semi-automated, so there is one manual step in there. And you also have the possibility to do the other steps manually if you want to. So you have the tight control of really what is happening at each step. But you can also just, for starting out, you can let do the program most of the steps automatically to get a first process data set and then verify the data set afterwards. Yep. This afternoon there's a hands-on exercise part of you already had it yesterday. What we will do there is basically set up a new project with a set of diffraction patterns, adding these to the project, also define the beam stop mask for these patterns. And then second part is manual verification of the lattices, so tweaking lattices within the IPLT lattice overlay. With this, I basically come to the end of my talk. I would like to thank the people that were involved. So, as I said already in the first talk, where I was talking more generally about IPLT, here in Boston, in Tom's lab, where I am now, it's mostly Richard Hyde, which now basically tests all the things I do and uses it for his data sets and gives me immediate feedback if things are working. And Tom is very supportive, giving me time to develop the IPLT, do diffraction processing, test it, and also verify it with data sets we have in the lab. There are Mariani and Marco Piazzini. They were together with me and with Ansgar and Andreas Engel's lab, where we started the IPLT program, where we started developing that. They are still helping me with testing and also with helping it to create packages and if there are questions. Same as with Ansgar Philipsen. He did most of the algorithms for the diffraction processing were coded by him. So I basically now just put them together into the graphical user interface and also tweak some of them. And then I'm also very thankful to all the people that at one stage or another gave us the data set to test parts of IPLT. So we got data sets from Japan, one from Stockholm, one from Berkeley. And I'm also very thankful to all the people here in the SINA and before we were here in the SINA and MEH, which provided feedback on the software. And also very thankful to Andreas Engel because he, for a very long time now, basically supported IPLT, made it possible that we really spent that time to get a really nice framework on top of which we now can build the graphical user interface and get this nice diffraction processing done. Funding is currently by the Swiss National Science Foundation, so I got a fellowship from the Swiss National Science Foundation to further develop the IPLT, and also basically by Harvard Medical School by Tom. He's supporting me to be able to do this. With this, I would like to thank you for your attention, and if there are questions, feel free to ask. Yes?
A couple of questions.
Yep.
Do you have to deal with pincushion or barrel distortion?
Yes. I haven't mentioned that, but you can actually, in IPLT, you can fit a pincushion and barrel distortion. You could also do it manually in the manual interface where you can manually fit the lattice. But from what I saw, for most of the diffraction patterns, the distortion is very small. So unless you have an off-axis DCD, the distortion is normally very small.
My other question is, let's say you've got collected some data on film. Do you have a correction for non-linearity in the measurement?
No, this we currently don't have. Because all the data sets we had so far were all CCD. Yeah. No, that's something that's still missing. If you would record data on film and would need to process that, that's not in yet. Yeah.
When you have all the background values, but you're a little bit off with your zero, can you correct automatically for activity of 1 unit cell?
If your office is here and you have...
I mean, then you would not be on the right circle if you would take, well, I made a very condensed question. So theoretically, if you were off by, say, 1 unit cell.
Yeah. So that here, wait, let's quickly go to the image. So basically, if this one here would be off by 1 unit cell.
Right. Now, basically, from your lattice, the lattice points which are sort of on a circle.
Mm-hmm.
And if you would go to that circle and you would now look at the background values you have,
mm-hmm.
then of course if you are not hitting the right zero,
the background values would be different.
Would not be equal. They would have an enormous sigma. And the question is whether you could automatically correct for that, just using this information.
Yeah, that's actually a very good idea. I think this should work, yeah. I think this could be done. So it's not yet implemented. Currently, it's just basically the origin is found before the lattice, and then,
right.
And for most of the cases, it hits it. It's sometimes off by 1 or so. But that's true. That this would be another verification that you can do automatically. Additionally, to just get more of the patterns correct from beginning. Yeah, that's true. That's a very good idea.
I want to ask, how do you deal with the missing spot problems due to the symmetric feature? For example, if the crystal is the sentence, it may be missing spot. So in this case, how do you detect the lattice, or do you deal with this problem?
So if you have missing spots, so if you you probably could be then just IPT gets you the big lattice automatically. But I mean, you always in these cases you always have the chance to set it correct here in the verification step. It's quite easy to half or double the size of one of the lattice. So if it's done wrong in the automatic processing, because basically the automatic lattice determination doesn't know anything about the symmetry. So all it does, it tries to find all the peaks that are around and tries to fit a lattice that fits on all of these peaks. Yeah. You only know this in the later step, yeah. Yeah. Yeah.
Although obviously you look at it afterwards, and that was the pre-program back also.
Pre-coder.
The background of the elastic connector, and then auto index, which is similar to what you described, because it puts every detected spot in the middle, and then adds the density, so that's a spiral scan to get the lattice.
Yeah.
And then the pre-program takes auto, which is a simple mask integrated with background, and then the profile, which is copied from all the algorithms from the X-ray people, and evolved a profile that varies depending on the position. For example, along the field axis, you have sharp profile, and then perpendicular to it, it gets fuzzier and fuzzier. And those profiles are learned by the program. So, I think if you wanted to use them, you'd have to take those three programs and just test them out on a few standard films. As far as we know, they're still fine. And there's one thing, is that was the indexing on the highly tilted pictures, which again you said is tricky.
Yeah.
Let's say it's a 60-degree tilt, and you don't quite know where the tilt axis is. There are often 2 or 3 possible indexing choices. As I remember, one of the programs, the orange tilt, was something called reindex, which tries out all the various reindexing, which it takes the index you've done, and then it redoes it according to a certain range of possibilities, and compares them to the existing 3D matrix of lattice lines, and finds one that's best again for the
Mm-hmm.
in the way here emphasized the ultra-critical and don't believe anything. So they are there, and actually if people wanted them, would take that wrong step. Fully external combination, they are supposed to be in our lab. We do check that they all compile.
Mm-hmm.
We don't necessarily do standard runs to check that the answers are still working on every program.
Mm-hmm.
We're doing it only on the ones that people are still actively using on tools.
Mm-hmm.
Yeah, profile fitting is better because for example, if it's still we have overload,
Uh-huh.
but you have different statistics on the weak bits, the strong bits, and the spot. And profile fitting does the proper weighting,
Mm-hmm.
whereas simple raster integrating and then having background active, in a way, gives equal weight to a bit of the spot that's strong and a bit of the spot that's almost at the tail end that doesn't really matter. Whereas profile fitting gives very little weight to the bit of the tail and
Mm-hmm.
more weight. So it's very good. You learn the profile on it's mostly learned from the strong spot,
Mm-hmm.
the average of all of them. And the effect of it is most cells on the weak spot. So you probably get a factor of 2
Or the weak spots.
on weak spots by using profiles that have been learned from the strong spot. Right?
Mm-hmm.
And all the X-ray people, I mean, there's nobody not using profiles.
Mm-hmm.
So I think it's a way. So there are more parameters, and of course, therefore there are more things to go wrong.
Yeah.
And that picture is obviously a lovely picture. Any program will be able to integrate that. But if you get flakier and flakier,
Yeah, then you might profit from profiling. Yeah.
then you basically don't want to use anything automatic. You want to do everything manually.
Yeah.
All right. I think on that note, I'd like to finish, and we'll have a short coffee break now. First, thank Andreas, of course, again. And then let's be back in 10 minutes so we don't get too far off schedule. Thanks.